So this is 3.3, vision and hearing. The objective today is you'll be able to determine how important perceptual interpretation is to our experiences. So how do we see? Over to the right here, you have your eye, and you can get a better idea of how vision works. So we have a candle flame. It travels in through the cornea, through the opening in your eye, your pupil. It is then focused via your lens onto your retina. And the retina is a stamp-like structure on the back of your eye. As you can see, the picture is, or the image is actually upside down and focused primarily on the fova. The fova, you need to write this down because it's not in your notes. So write this down. The fova is a place of increased cones. So you have more detail, or you see more detail in this part of your eye, the fova. That information is then transmitted down to your optic nerve, where the information travels to your visual cortex. Now, and the occipital lobe. Now, where the blind spot is, you have a blind spot right here. It's where the optic nerve actually attaches to the back of your retina. There is no vision receptors right there, so you don't actually see anything if that appears on your blind spot. The reason why we don't ever notice it is because our eyes are constantly adjusting, and we have closure. It fills in the blanks for whatever we might be missing. Vision is described by transduction, where light turns into neural energy or neural messages on the retina. There's three aspects to light. First, you have brightness, and brightness is determined by the height of the light wave. So however tall the light wave is means how bright it is. Hue, or the depth of the color, is the length of the wave. And then the saturation of a color is mixture of wavelengths. So however the wavelengths are mixed shows us saturation. So we have these wavelengths, they're traveling in through our eye. So how exactly do we see? Well, it's because, like I described earlier, we have the light enters right in through your lens and then travels to the back onto your retina. And this visual accommodation allows you to focus on items close and far away. So if this candle were to move further away or closer together, when that moves, we have what we call visual accommodation, and your eyes accommodate for that distance. As I described, the blind spot is where the optic nerve enters into the back of the eye. And the way that we process information, so the back of your eye is full of what we call rods and cones, which we'll get into here in just a minute. But how we process that information is your retina has rods and cones. Those rods and cones take information. They pass that information along to your bipolar cells, which then transmit them to your ganglion cells, which then eventually will take them down to the optic nerve. So behind your retina here is a variety of cells that are passing that information along to your optic nerve. And we have found that there was a critical period for the sight to develop, that if you were born blind and then you gain your sight back, after infancy, it's difficult for people to understand shapes or have a full understanding of shapes. So they can see, but they don't have a full understanding of shapes. We believe that's because your brain has a specific critical period for understanding that. So how do we see brightness and color? Well, we see brightness because of rods. So rods are in the back of your eye on your retina, and they're what allow you to see black and white. You have dark adaptations. So if I turn off the light on you, it might seem really dark at first, but then your eyes would begin to adjust and they would adapt to the darkness. When you turn on the lights, same thing happens. Light adaptation, your eyes adapt to the light. How do we see color? We see color because of cones on the back of your eyes, where the retina are on the retina, where we have rods. We also have a significant amount of cones. And these cones allow us to see color, and there's two theories. The first is the trichromatic theory. This is that we see red, green, and blue, and then combinations of those three colors. However, what it does not explain is what we call the after image. Opponent process theory says that cones have pairs that cannot fire at the same time. So you have colors that will fire one at a time, and those are in the red, green, yellow, blue, white, and black. And what this helps us explain is what we call an after image. So if you were to stare at a red dot for a really long time and look at a white piece of paper, you're going to see a green dot, and that's because of after image. The image remains after the stimulus has been removed. Color blindness is it's a genetic deficit in your cones, passed down through to males. So looking at the circle to the left, seeing the green 5 inside the color of orange, red, and yellow dots is a very simple test that they do for color blindness. Perceptual consistency. Perceiving objects as unchanging allows us to recognize items quickly. We have what we call shape and size consistency, and you've already had a couple questions on this. I realize that I put them on there before you've talked about it, but it gave you guys a little bit of a preemptive information. This idea that with size, if we see a car far away, we still know that a car is a car. We still know the size of it. We still know it's big and people can fit into it. Same with the shape. If you are standing there and watching a door open and close, that shape of the door changes how you see it, but you still know that the shape of the door is the shape of a door. It's still, a rectangle or whatever it might be for that door. This also exists for color. We perceive familiar objects as having a constant color. So, for example, we perceive school buses as yellow. Even if we were to see it at night and it's dark and you can't really get the full yellow effect, you know that it's yellow. Something else that's kind of interesting is if you take a look over here, that color constancy can change depending on what's surrounding it. So really, B and A are the exact same color. I know, it's crazy. You can print it out and cut it out and put them next to each other if you want. They're the same color, trust me. But it's just based off of what's around it that makes it, alters it, or makes it look different. Another good example is if you put tinted glasses on, and after a moment, everything looks the same color as it did before. So if you had like green tinted glasses or yellow tinted glasses, and you put those on, it's going to look really yellow for a minute, but then eventually things are going to go back to normal. Visual information processing. So how do we process this information? We have what we call feature detectors. Feature detectors are located in your occipital cortex, so in the back of your brain. And this is the ability to respond to a scene's specific features. So for example, it allows you to identify faces because of the edges, lines, angles, and movement of that face. So that's how you're able to detect that feature. And parallel processing plays a role in this because as your brain is understanding these feature detectors, you're actually doing what we call parallel processing, meaning that your brain is noticing multiple things at one time, such as color, movement, all at the same time of one another. And if you take a look to the right-hand side, this is how we go from sensations, the idea of seeing something, to quote-unquote recognizing that item. Okay, the process of hearing. So to the right here, you have an ear, and actually on your Nearpod, you will have a 3D image of an ear, so you can kind of get a better look of what this looks like. So how is it that we hear? Well, first, pitch is, again, sound waves. So as sound waves are entering your ear, we understand pitch by how fast those sound waves enter, so the frequency of that wave. We understand volume because of the amplitude of that wave. And we understand what we call timbre by the purity of that wave. So how is that wave interfered with anything else? We hear about 20 to 20,000 hertz or waves per second. And the way that we hear is the sound wave is going to travel in through your ear, it's going to hit what we call the eardrum and then vibrate through the middle ear, which are the 3 bones right here, the hammer, the anvil, and the stirrup, are these 3 little bones that are all connected to the eardrum. So as that sound wave hits the eardrum, it causes these 3 bones to vibrate, which sends messages then through the semicircular canals into your inner ear, your cochlea, and then out through your cochlear nerve. We can tell the location of a sound because often it is detected in one ear slightly before the other ear, so therefore we know where sound is coming from. How is it that we hear exactly? Well, there's a couple theories. The first is that place theory, that these sound waves are traveling in through your ear, traveling and vibrating, and then wherever that sound wave hits on your cochlea, has an idea of, gives us an understanding of pitch and understanding of sound. Frequency theory is the idea that inside of your cochlea here, you have what we call the basilar membrane. Basilar membrane are microscopic hairs that line the inside of your cochlea. And the idea here is that the way these basilar membranes vibrate, or how fast they vibrate, the frequency of them vibrating, is another way for you to understand or quote unquote hear. And what we call this is volley, that hair cells take turns firing. And these aren't like the old grandpa ears or ear hair that you have out here. These are tiny microscopic hairs that you have on the inside of the cochlea right here. So what happens when you lose your hearing? Well, it happens one of 2 ways, either conduction hearing loss or sensory neural hearing loss. Conduction is when there's been damage to the hammer, the anvil, the stirrup, or the eardrum. And so therefore there's no vibrations happening. Sensory neural is when either disease or biological changes, so things as you get older, as you age, prolonged listening to loud music inside of your earbuds, that is sensory neural hearing loss, which can be corrected by a cochlear implant, which is what an electronic device that translates sound into electrical signals. Remember, neurons, so we're talking electrical, that can transmit information via the cochlear nerves. Some people have what we call, and I'm going to mispronounce this and I apologize, synesthesia, which is when one sensation can produce another. So for example, when you hear certain sounds, you might see specific colors. And this is, again, due to neural communication between your senses. And that is it for today.